Hello everyone, I'm Yan Chao from NCC University and System Research at Google. I will introduce our work called the Software Persistent Memory. The Intel Optane DC has commercialized for several years, and this kind of hard PMM hasn't become ubiquitous in the data centers since the hardware revolutions in 2014. And basically that is because the following three reasons. One is that the hard PMM has a lower performance than the DRAM, and the system software and the application need to be redesigned to, on the one hand, enjoying the direct addressable persistency benefits. On the other hand, they also need to mitigate the lower performance of the hard PMM lower performance of the hard PMM than the DRAM. And in this work, we look into another solution to enjoying the directly addressable persistency. In the current large-scale, well-engineered data centers, they will basically have the battery rack, and this battery rack can provide the power upon the power failure, and this can make the data center tolerant to the power lift, and also that can provide the controlled slowdown, shutdown, and the NVDRAM would be add-on features on the existing battery rack system. So in this work, when we are saying the NVDRAM, we mean the conventional large DRAM like the DDR4 with the typically rack scale battery backup. And this NVDRAM will have the following features. First is that it also have the directly addressable persistency. Second, that would have the real DRAM performance. But the limitation is that it have the limited capacity. We'll explain that in the next slides. And in this work, we will explore two questions. First, can NVDRAM accelerate the adoption of the hard PMM? Second, whether the NVDRAM perform better than the hard PMM, which would provide another options for the current usage. The NVDRAM limitation is the bounded save window. Basically, upon the power failure, the battery rack would provide the power for the part of the DRAM, which is the persistent region assumed in the system, and that is corresponding to the NVDRAM region. And then within this limited power, the system would flush some content, which is the execution stage, into the storage. And the size of this region, we call that as the save window size, which is the flash time multiplied the storage bandwidth, which is about like tens of gigabytes. And all the NVDRAM system need to ensure that the execution stage that needs to be saved should be always smaller or equal to this save window size. Otherwise, the NVDRAM system would not really provide the persistency. And we explore these questions from the application persistency model. The application has utilized the persistency for decades. Typically, the transactional semantics require logs in addition to the primary data objects. Normal operations are performed both on the objects and the logs, and the logs are periodically flushed to the storage, and those log regions are necessary for the persistency. And upon a power failure, the in-memory objects can be restored from the old version, which is potentially a snapshot, and then the logs are replayed to restore the old version into a relatively newer version to provide the persistency. And in general, the hard PMM pre-propose a particular persistency model, what we call as the large in-memory persistency. But the SoftPM is flexible because that is built from the conventional general-purpose hardware. So the methodology of investigating this would be important. So we actually first investigate the application persistent model to extract the dominant persistency models and that are used in the application. And then we structure the system infrastructure accordingly to, on the one hand, manage the hardware, including the NVDRAM and the storage. And on the other hand, we provide the interface for different persistent model to make the them can easily be ported to by using this SoftPM system. And we will go through that in this talk. And meanwhile, in this work, we will focus on the performance under the normal operations. Restoration on failure is essentially the same as in the conventional scenario, like persistent data to the SSD. The subsequent content would include the application persistence model, SoftPM design and implementation, multiple versions of Redis, and the evaluation. We classify the persistence model into 3 scenarios. First is the static model. In this case, the application will fully manage the fixed size region, and we use the one database work as an example to illustrate this. The application would have the logger, which will need to write the logs of the incoming request. And then this logger would first request the log buffer from the free buffer pools. After it finishes writing, that will return this buffer to the flashing buffer pool. And the background flash will actively flash the content in the flashing buffer pool. And in this kind of design, actually they provide the guarantee that the application will at most lose a fixed size data upon the power failure. Because if there's the free buffer pool is used up, the application needs to suspend until the reclamation of the flashed buffer. And in the second scheme, which is the append-only persistence model, we use the Redis as the example. So in this case, the application constantly append the log to the in-memory region, and this content will be periodically flashed to the storage. So in this design, actually, that provides the persistence guarantee is that the application will lost a certain time of the progress if a power failure happen. And the third scheme is the large in-memory persistency, which is assumed in the most of the hard PMM research. And in this persistence model, they assume that as long as the data is flashed from the cache to the memory, then the data is persistent, and the benefit is that they can even maybe reduce or remove the logs to have a better performance. So in the SoftPM system, we structure the system infrastructure accordingly to provide 3 sets of the interface for these three different persistency models. First, we introduce the SoftPM static, which are designed for the static persistency model. So in this case, we will tag all allocated persistent region as the save window region. So we implement the user space SoftPM and the kernel space SoftPM. And when the application needs to allocate the persistent region that will use the pmalloc and free to the free list, and then that will invoke the related map calls. And after the application acquire this region, it can perform the store, reclaim, and flash of this persistence region. And then if a power failure happen, all the pages are tagged as the SoftPM pages will be flashed into the storage. And the second scheme is the user-directed one. So this is designed for the append-only persistency. So what we are find is that the appended log will not be overwritten again in the append-only persistency model. So in this case, we design the background flashing, and the user can deliver the read-only hits to the SoftPM system to help this background flashing. And that will, because the SoftPM size will constantly growing when they append the log. So we have the save window size control to make sure the total save region is smaller than the save window. And we implemented the user space and the kernel space SoftPM, and in the user space we further introduce the daemon thread and to perform the background flashing. And when the application allocates the log buffers from the free list, and then it can perform the write for each logs. When it finishes the log writing of one buffer, it can notify the daemon thread by using the pready to let the daemon thread to perform the active flashing of this log to the storage. And after it finishes the flashing, it can return this buffer into the free list. And if the new allocation will exceed the save window size, we will suspend the application execution until the flashing is finished to control the save window size. And if a power failure happens, all the SoftPM pages will be flashed into the storage to provide the persistency. The third scheme is designed for the large in-memory persistency, which is the SoftPM transparent. The design is that we use the dirtiness-aware save window size control, and we also use the user-transparent background flashing. So in this design, all the pages are not initially need to be flashed at the allocation. So if a power failure happens, we will only flash the dirty content into the storage, and that will help us to save the save window to adopt to the larger in-memory persistency model. And if the total dirty pages is close to a threshold, the dirty page manager will select some code dirty pages into the daemon thread, and the daemon thread would flash those data and then update the dirty bit in the page table and also the dirty page manager to update the current dirty page state. And if a power failure happens, only the dirty pages in the SoftPM will be flashed into the storage to provide the persistency. And then we will introduce a little bit about the SoftPM transparent implementation. So all the SoftPM pages are tagged as write protected initially, and if there's a write happen, that will be trapped to a customized page port handler. In this handler, we will check whether the dirty pages is equal to the save window. If that is not, we will unset the write protect bit and then add this page into the list that needs to be flashed. And if that is, we will wait for finishing one page flash, and then we will unset the bit and add that into the list again. And meanwhile, in the dirty page manager, that will periodically scan, clean, and record all dirty pages reference bit to see whether that is recently used. And if the total dirty pages is larger than a threshold, we will flash the LRU pages until the total dirty pages is smaller than the threshold, and then we will set the write protect bit for all flashed pages. And we implement that in the kernel space to fulfill those design. Next, we will introduce the multiple versions of the Redis that will port. Some of them is designed for the hard PMM, and some of them are designed to the soft PMM. The first scheme is the baseline scheme, which will only use the DRAM and the SSD. So in this case, they will put all the data and the value in the DRAM, and the read request will directly go to those keys and value and retrieve the corresponding content. For the write related request, that will first record this request in the log, and then that will apply the changes to the data. And the logs will be periodically flashed to the storage to achieve the persistency. And we use in the SoftPM user-directed design, we based on this original Redis. The differences is that we will put the log on the SoftPM region such that that can provide the persistency of these logs, and that's only require about 100 lines of code changes to let the original Redis to use the SoftPM system. And then the third scheme is the hard PMM version. So in this scheme, actually, because the data is persistent as long as that reach the memory. So in this case, they can discard the original logic to achieve a better performance. They can directly do the in-place update for the key and values the in the in the hard PMM, and because the hard PMM performance is not as good as the DRAM, so they further design the hybrid scheme, which would basically apply two optimizations. One is the append only a pointer based append only the persistency, and the second is the persistent ring buffer. So in this design, this first separates the key and the value. The keys and the indexing data structures are stored in the DRAM, and the values are stored in the PMEM. For the read-related request, that will go to the DRAM to find the corresponding address of the value, and then retrieve the value from the hard PMEM. For the write request, that also would first find the corresponding address and then update the value in the hard PMEM case. But there are also some write-related requests that would update the key. So in that case, if they directly update the key in the DRAM, so that cannot really guarantee the persistency. So what they are doing is that they also write the log in the hard PMEM, which are stored in the persistent ring buffer. In this log, that will insert the key and also the value pointer, and the update. If this request also updates the value, that will happen in the hard PMEM. And to limit the hard PMEM usage for the log, they will periodically flash this log in the SSD to save the hard PMEM usage. So in this design, what you can find is that applies several fancy optimization to really provide to mitigate the hard PMEM performance inefficiency. And in our fifth design, we the SoftPM transparent, we only port the code to use the hard PMM version rather than this hybrid version, because with the NVDRAM, actually those optimization in the hybrid are not necessary to be used it's not necessary to be used. So we can use a very clean design, but that would provide a better performance. So the summary of the multiple version of the Redis are shown in the following. Only the first scheme will provide the per second persistency. All the other scheme will provide the per record persistency. And the first three scheme will use the Redis code base, and the fourth and the sixth scheme use the 4 PMM Redis, and the hybrid scheme use the hybrid Redis. Our evaluation is conducted in the following machine, which is we will use the 6-channel hard PMM and the 6-channel DRAM and SSD. All server and the client threads are running on different cores on one circuit, and we conduct the evaluation on unlimited save window size and the limited save window size. For the micro benchmark evaluation, so we can first look into the first three scheme, which is corresponding to the baseline every second persistency, baseline always, and the SoftPM user directed. What you can find is that the always persistency actually incurs a large overhead to really achieve the per record persistency. But by using the SoftPM system, that can achieve both per record persistency but also a better performance. So that is because that will provide the background flashing and that will don't need to fsync every record write. And for the later, and then we can look into the later three scheme, the hybrid, the hard PMM hybrid and the SoftPM transparent. So in this case, what you can find is that even for the set request, the hard PMM scheme is even though the hybrid scheme is performs better than the hard PMM scheme, but that is still far away from the soft PMM transparent. That is because the soft PMM transparent would really have a DRAM performance the byte addressable persistency, and that will have a cleaner design to further improve its performance. And overall, the SoftPM transparent can improve 7% to 88% throughput over the hybrid scheme. And then we conduct the evaluation on the YCSB workload. For the update heavy request, for the update heavy workload, what we can find is that the SoftPM scheme and the hard PMM scheme would be its performance are separated into two tiers, and both the SoftPM scheme would perform better than the hybrid and the hard PMM scheme, and that would also exhibit this two-tier performance gap in the read mostly scheme. So overall, the SoftPM transparent can improve 40 to 90% throughput over the hybrid scheme. When we limit the same window, what we can find is that in the read mostly and read only scheme, the performance is similar with the unlimited case. And for the heavily updated scheme, actually the transparent case will suffer from the performance, will have some performance reduction, but the user directed scheme will still be close to the unlimited scheme. That is because the user directed scheme will perform the actively flashing as long as there's a log ready, and meanwhile there's no write amplification. So that is also the reason why the transparent case would have some more overhead. And overall, the SoftPM scheme would incur at most 9% overhead even with 10% save window size. In conclusion, the SoftPM is potentially available using the techniques already provisioned in the data centers today, and that can provide 38 to 93% throughput over the well-optimized hybrid scheme. That is because it has real DRAM performance, memory, and background flashing, and the cleaner designs. And the SoftPM would also set the performance bar that the future hard PMM and its ecosystem need to beat. And that's all of this talk, and I'm happy to take questions.